we're going to have a look today at some more functional groups, and then we're going to move on to talk in detail today about alkanes. That's going to be the big chunk of the lesson before we do some practicing at the end. But we haven't yet talked about carboxylic acids, so let's do that first of all. And so this carboxylic acid is the name of the homologous series. And I'll remind you, I'm not going to practice it right now, but we've learned what we mean by homologous series, this idea that a family of molecules that have the same functional group and differ by CH2 within that family. So you go from, for example, ethanol to methanol, ethanol, propanol, butanol, and all of that kind of stuff. And we do the same thing within the carboxylic acids. So the name of the family is the carboxylic acids. The name of the functional group is new to you though. So the functional group is called, and it's on the sheets I've just given you as well, but we'll call it from now on a carboxyl. So carboxylic acid is a carboxyl functional group. And we write the carboxyl functional group like this. So we have a line going to whatever the rest of the molecule would be, and then a carbon double bonded to an oxygen, and that same carbon bonded to another oxygen singly, and then there's an H there. Now the rest of the molecule I'm going to represent with the letter R, and you'll see me do that quite a lot. So that's just the rest of the molecule, and that could be an H or it could be a carbon chain of some sort. So it could be anything within that family. And because of the way they're structured, look at the carbon here has got 3 of its 4 bonds to oxygen, and so you're always going to get carboxylic acids at the end of a chain, right? So they're all, we call them, it's not a word you need to use, but they're all terminal functional groups. They're at the end of the chain, so end of chain, of course. Right. So you should be familiar with these because you've seen them before. And I always like to, as I think I was saying last time, put lone pairs on oxygens to just remind you that oxygens have always got 2 lone pairs, and that helps us remember why it is that things like alcohols and carboxylic acids make hydrogen bonds, because they've got hydrogen bond acceptors, which are those highly electronegative oxygens with lone pairs on them, which is what you need to make hydrogen bonds, right? And we've got hydrogen attached to an oxygen. So they've got relatively high, not high, but relatively high boiling points, as can make, you can turn it into proper English if you want to, as can make hydrogen bonds as well as London forces and dipole-dipole. Okay, so, but they're even stronger hydrogen bonds than with ethanol, because you've got 2 oxygens, 2 hydrogen bond acceptors there, which mean that it can really make a very strong hydrogen bond network, and you end up with quite high boiling points. They're also typically quite soluble in water for the same reason. Because they can make hydrogen bonds with the water through the oxygens or through the hydrogens, so they're very soluble in water typically. Soluble, sorry, I should have written that down before. Okay? Right. As far as carboxylic acids are concerned, that's all we're going to do for now. I'm just going to ask you a question based on last time. Those not here or haven't watched the video yet, ignore this. But if I draw a circle around that C double bond O, what might we also be tempted to call that? That's what I wanted you to say, but it's wrong. And I wanted you to say it because I wanted to point out that it's wrong. Now, what we learned last time is the C double bond O is only a carbonyl when it's in a ketone or an aldehyde. So when there's H's and carbons there. So watch out for that. So it is a C double bond O, but the C double bond O behaves very differently in a carboxylic acid to when it in an aldehyde or a ketone. So thank you for deliberately making the mistake. I'll set you up for that earlier on. Okay? That's that one. We're going to move on. You with me? Following that? Okay. And we'll come back to carboxylic acids. We'll learn about how they can be made from oxidation of alcohols, and we can learn how they're... Can I just have ice? This way, please. And we'll learn how they react to form esters and all that kind of stuff. So should we do esters next then? Again, you might remember ester from last year, some of you, because we learnt esters last year. Now they're very closely related to carboxylic acids. The only difference between esters and carboxylic acids, and by the way, the homologous series and the functional group is called ester. I call it esters. But the only difference is that we've got, instead of the H there, which gives carboxylic acids that characteristic acidic property with pH as a weakly acidic, so pH maybe 4 typically for carboxylic acids. Instead of the H there'd be a carbon chain, which we're going to represent with the letter R again, but with a dash this time to differentiate it from the other R. So if we just put R and R dash equal carbon chain. So for example, I'm going to draw one ester just to show you. I'm not going to do any more than that today. So that's an example of an ester. Notice the H has gone and we've replaced it with a carbon chain, a short carbon chain. It's a methyl carbon chain, isn't it, over here? So we call this one methyl because that's what and the naming of esters you don't need to know, by the way, but they're quite straightforward to name. So methyl, because there's a methyl group over there, one carbon. And the bit I do want you to know is that ethanoic acid, which that would have come from, when it goes from an acid to an ester, we call it ethanoate instead of ethanoic acid. So it's very similar. So there's methyl, because the methyl over here, ethan, because 2 carbons, no double bonds between carbons, O8, because it's an ester, methyl ethanoate. And these typically have lower boiling points than acids. Discuss. I'm going to do discussion slightly differently from now on. I'm just going to pause this. Right, good. So you just said there that esters typically have slightly lower boiling points than carboxylic acids because they don't have a hydrogen bond donor and therefore can't make hydrogen bonds. So give me a thumbs up if between you in the end you got that kind of an answer in your discussions. Good, nice, right. The phenyl group we're really not going to spend any time on at all right now. But phenyl group, you will see it now and again. You will see this funky thing attached to a chain of some sort or a molecule of some sort. And we're going to talk about that thing, the aromatic ring. Sometimes chemists label it AR, but you're probably not going to see that. And sometimes you see it drawn like this too. And we'll learn about bonding within something called benzene in quite a lot of detail. So we'll get to know this quite well. So it's really, I don't want to spend time on it now. The thing I'm introducing to you, what I'm introducing to you now is that we call this a phenyl group if it's a functional group. So phenyl functional group, and you'll find this in aromatics. So that's the functional group. Anything where you've got these 6-membered rings with 3 double bonds or this circle of delocalized electrons that we'll talk about, we call those the aromatics. Okay, so that obviously comes from the fact that there's obviously a distinctive smell of some sort when they were first named, but it's got nothing to do with the smell these days. Whenever you see that 6-membered ring, we'll talk about them being aromatics and having a phenyl functional group. That's it on that. We talked about amines last time, right? Yeah, we talked about amines. Can I all ask you, we're going to do a bit of mini whiteboard stuff. We're going to do a bit of mini whiteboard stuff. Can you all draw on your pages, on your mini whiteboards, a primary and a secondary and a tertiary amine? Go. So carboxamides, or amides as I mostly call them, are sort of related to amines and sort of related to carboxylic acids. Okay, so they're a bit of both. I would say that actually they're more, well, it doesn't really matter what they're more related to. It doesn't matter. Let's just draw one. So again, I'm going to draw R for the rest of the molecule. And up to this point, it's exactly the same as a carboxylic acid. But whenever we say AM in chemistry, amine, ammonia, amide, think ammonia. That am is telling you there's a nitrogen present, right? So amines. And so we've got a nitrogen here instead of that oxygen. And of course, nitrogens make 3 bonds, and 2 of those bonds might be hydrogens, but they could be carbon chains as well. And there's a lone pair on there. So that's what an amide might look like. They could also be something like this as well, where you've got a carbon chain coming off that nitrogen. But the key thing is you spot and recognize and can draw, we've got a nitrogen attached to the carbon-oxygen double bond. You could argue that it's most related to esters, in fact, where you can see how this relates to an ester. If you swap that nitrogen for an oxygen, it would be an ester, wouldn't it? So it's really similar to esters. And at the start of every lesson, or at some point in every lesson, I'll be practicing these functional groups with you. I'm afraid you just need to know them, and it's going to be problematic for the rest of it. The rest of organic chemistry is fine if you know the functional groups, and we're going to practice it lots in class and outside of class. But you need to know the functional groups. I can't help you if you don't know them. So if I say right now draw an aldehyde and you can't, it's going to be a problem. So we'll get onto that when everyone's back and when you've all had a chance to catch up with lessons that you've missed due to D&V or whatever else has been going on. All right. So then let's move on. Let's now talk about, so that's all of the functional groups now. We've been through all of them you need to know, which is good. So you've got that in the bank and you just need to learn them. But now we're going to spend time learning about alkanes. Now some of this stuff you've learned at GCSE again. We know all about alkanes. I'm not going to teach you alkanes from scratch again. We did what they are the other day. But it's going to be the reactions of alkanes today. And remember that alkanes haven't really got a functional group to speak of. I mean, they haven't got anything interesting going on. They've only got carbon-carbon single bonds and carbon-hydrogen single bonds, right? So they don't get up to all that much chemistry because they haven't got anything interesting they can really do. You know, for example, already they don't react with bromine water, which you learnt at GCSE. They do, though, and you know this as well, they burn, don't they? We use them as fuel, so they undergo combustion. So that's the first thing I need to remind you. And when you look at the slides, if you decide to look at the slides, you'll see there's a whole load of stuff on practicing enthalpy changes of combustion and all that kind of stuff. So combustion, so we've got our hydrocarbon, and let's just pick one, let's use butane. And react with oxygen, and it will give you carbon dioxide, of course, and water. And that will give you 4 carbon dioxides and 10 waters. All we've got to do is work out how many oxygens there are now. So we'll need 6.5 to make that balance, I think. Someone just check that for me. Okay. So that's the equation for combustion. But this is complete combustion, right? So could person A, out in your pair, say what we mean by complete combustion, under what circumstances that happens? So you're right, I can hear it lots of times around the room, when there's sufficient oxygen, so excess or sufficient, sometimes write excess shorthand like that. What this means is that the carbons are all fully oxidized to carbon dioxide and the hydrogens are all fully oxidized to water. This point, can I make it again? Can I just have eyes front for a second? This idea that hydrogen atoms within alkanes are oxidized to water is a point that's often missed by people. People often draw hydrogen as a product of combustion. Hydrogen is explosive. If you make hydrogen in a fire, it will explode. And so it will just turn into water. So the carbon's oxidized, the hydrogen's oxidized. That's what complete combustion is. And fully oxidized hydrogen is water, right? But you can also get incomplete combustion as well, which is when, of course, we've got a lack of oxygen, though some might be present. And I'm not going to make any attempt to balance this because the balancing of it depends on the ratio of oxygen to butane that you've got. But the products you can get, you still get water, You always get water still. The hydrogens are still oxidized, and they're the first things to be oxidized, really. But in addition to the carbon dioxide, you'll get varying quantities of carbon monoxide and carbon soot as well. And I'm not going to spend any time on the stuff we did at GCSE about carbon monoxide being toxic, and this stuff being soot and having problems associated with it, because you know all that stuff really well. Okay, but that's it for reminding you of that. If you need to look back over it, by all means do so. But this is when you've got partial oxidation. Let's write that down at least. Partial oxidation of the carbon atoms. So instead of being converted to be fully oxidized to carbon dioxide, where the oxidation number is what, person B? What's the oxidation number of carbon in carbon dioxide? Tell your partner. Yeah, it's +4. Heard it a few times. Person A, what's the oxidation number of carbon in carbon monoxide? What's the answer? Yeah. And what's the oxidation number of carbon over here? Please show me with fingers, everybody. Yeah, 0. So you can see that where carbon isn't fully oxidized, you end up with carbon 4 plus, carbon 2 plus, and carbon 0. And as a bonus, then what's the oxidation number of carbon and butane? It's competition. Whoever gets there first gets a high five from Cameron. So minus 2.5 over here. You can see the carbon's been oxidized. I'm trying to tie together for you bonding, and you see how you see what I'm trying to do, hopefully. And yeah, no, let's not do that. I haven't got time. I think last time I was doing stuff around shapes of molecules, bonding types, all that kind of stuff as well. We just don't have time today. Right, here's where the fun starts, though. So, can you write a heading? Let's start a new page. This could be fun. You're gonna need don't start at the bottom of a page here. Now, don't get upset if this feels like it's complicated. Listen really carefully to me talking you through this. Make really, really careful notes. Well, I promise you we'll practice it lots. Did you say I'm scared? Someone said I'm scared. Free radical substitution of alkanes, why not say with halogens? Specifically Br2 and Cl2. Right. So, what we're going to be learning about is a reaction where you can take any alkane, and I'm going to use methane to start with, but we'll practice with other ones. And you can react it with, say, bromine or chlorine. And you've been told they don't react, and that's true, unless, this is what you've not been told before, we're shining UV light at that reaction mixture. If we shine UV light at that reaction mixture, we get a substitution. And one of the hydrogens, at least in the first place, gets substituted with one of the bromines, and you of course are left with then one hydrogen and one bromine which combine to make HBr. So that is essentially what you have to learn. That doesn't look too bad, but the thing to remember is we need UV for this reaction to happen, because alkanes are unreactive and the UV allows this reaction to take place. All right. I'm going to let you catch up with your note making. Pens down when you're there, and then I can move on again, and I'll get you to catch up each time. So remember that alkanes are unreactive unless we shine UV at them. With bromine. You might remember that alkenes react with bromine very, very quickly, just a little shake with bromine water, and the bromine water goes colourless. This isn't true. This is much slower. So let me talk you through it bit by bit, and then make notes. Okay. So what's going on here? So what's going on is that the reaction is initiated by reaction of the bromine molecule. Okay, so what's happening there is bromine, of course, is Br2, and it's held together by a single bond. Bromines make one bond, and that's what a bromine molecule looks like. And this is a covalent bond, and you know that a covalent bond is a shared pair of electrons, and that line is representing 2 electrons, right? Because bromines are quite big, that bond is quite long. Because that bond is quite long, that bond is quite weak. Does that all kind of make... So you can, after all of that chatter, you can perhaps write this up as I'm going now. So bromine-bromine bonds are weak and long, or weak because they're long, because bromine atoms are large. And that means that those bromine-bromine bonds can break through a process called homologous cleavage or homologous fission. Homologous because you end up with two things the same. Homo, two things the same. You end up with two bromine atoms, which we call free radicals because they've got unpaired electrons, right? All they are is bromine atoms, but a free radical means it's got an unpaired electron. So if you like 7 in the outer shell, or in bromine's case, it's a bit more complicated than that, isn't it? Because it's a big atom, but if you like 17 in its outer shell, depending how you want to look at it. But anyway, it's got an unpaired electron in the outer shell, which means they're quite reactive. Which is why they're then suddenly able to react with very unreactive alkanes. For those watching on the video, while people are copying up, I was just saying that sunshine on our skin can cause damage through exactly this kind of process. Ultraviolet light can break single bonds in molecules in our bodies, and cause free radicals to form. Free radicals can cause damage to DNA and sometimes go on to cause cancer and things like that. So there are chemicals, if you learn in biology, that are good at absorbing free radicals as well and stopping cancer too. So one reason to eat certain vitamins is they're really good at absorbing free radicals too. Anyway, by the by. So the first step that you have to learn, and you would get 2 marks for this, is what I've put in the box there. So all of that is required to get 2 marks. 1 mark for showing the arrows, 1 mark for showing the UV in the overall equation, but you need to be able to draw that. Right, the next thing that happens, and it's a multi-stage reaction this, is propagation 1. It's called propagation because what we'll learn is there's 2 stages of propagation, and they happen again and again and again. For the reaction to proceed or propagate, it goes through propagation 1, propagation 2, propagation 1, propagation 2. So there's one initiation, and there might be a 10,000 propagation steps, propagation 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, over and over again until all the chemicals are used up, and then we'll learn at the end that there's some termination steps that stop the overall reaction. So what I'm going to do is walk you through what's going on. Again, I'd really like you to listen first and then write up afterwards. So what happens is these bromine atoms or bromine radicals are floating around the pot, right? So there might only be a few of them. It's not all of the bromine in the pot that's been turned into bromine radicals, just maybe a handful of them, maybe 1%, 0.5%, even less. It's an initiation process. You just trigger it and then away it goes. But what happens is some of those, and that point is really important, by the way, so we'll make it again. But you get a few of these bromine atoms. They will then bump into, or one of them will bump into an alkane molecule. And we're just going to represent, there are more complicated ways of drawing this, which you might see in books, but I want you to do it exactly as I'm showing you, because that will get you full marks, and it's the easiest way to get full marks, okay? I can show you longer versions of it if you want me to, but this is the easiest way to get full marks. So the bromine bumps into the methane. When it does, a process takes place where all it can really do to that methane molecule is grab a hydrogen off the outside of that methane molecule. So it rips the hydrogen off the outside. Because remember, I said alkanes are unreactive. Bromine radicals are so reactive they can do stuff to unreactive alkanes. So you're left then with CH3. Now I've taken a hydrogen atom away, so I'm left with this, which is called a methyl radical. I'll give you time to write up in a sec. But that methyl radical, radical. That methyl radical is a radical because it's got an unpaired electron. Just for interest, I'm going to show you what that would look like as a dot and cross diagram. So this bit of it's exactly the same as what we used to drawing for methane. Can you see that? Okay. Yeah. But there's an electron there that hasn't now paired up to make a bond. That electron has gone with the hydrogen, and the hydrogen has paired up with the bromine to make an HBr molecule. And notice that's one of the products we end up getting in our overall reaction. So we've now, in propagation 1, made one of the two products that we get in the overall reaction. And in propagation 2, of course, we're going to make the other product. Are you with me? Okay? Yep. Stick with me. I know it's probably all had a nice hot sunny weekend, but stay with me on this because it's tough. And we're going to do a little game in a minute, which I like. So propagation 2, though, is next. Do you want to write out propagation 1, or will I start writing out propagation 2? Then I'll talk you through it. As soon as you've written that all down, you drop your pens. So propagation 2 takes into account that we haven't yet used up all the bromine. Remember, there's lots of bromine and we only used a tiny bit of it. A really important point I made, and hopefully made quite clearly, that that initiation just used maybe 1%. Make a little note of that. Maybe 1%, just for argument's sake, a tiny amount of bromine has been converted to Br dot, Br radical. The rest of the bromine's still in there. And we've also made a few of these methyl radicals, and they're not one of the products, so they're going to be used up in step 2, right? So here's what happens. The bromine molecules that are still there, which is the majority of them, will bump into one of those methyl radicals that we've just made, and the methyl radical will pluck a bromine atom from Br2 to make the other product that we want in the end, which is bromomethane, and will generate, before you start writing it, we just finish the explanation, will generate or regenerate another Br radical, which can then go back up to here. Well, it's not the same one, it's a different Br dot, but this Br dot will then do this process with another methane molecule, making another methyl radical, which will react with another bromine to make CH3Br, generating another Br dot, which will then go on to make this reaction again. It goes 1, 2, 1, 2, 1,000 times, 100,000 times, whatever, till you end up with that. That's what keeps going on, right? And then that keeps going on until all of the reactants, all of the bromine and methane are used up, and then you end up with these termination steps. So you go ahead and start copying up propagation 2. And there are 3 possible termination steps that usually people find the termination steps easy to learn. All it is combination of 2 radicals to make a molecule that's not a radical. And these are just a tiny few reactions at the end. Go back to do this chemistry here. Only when things have run out, once the bromine starts to run out, the radicals will combine with one another. Oh, I made a mistake. I knew I would. Sorry, that bottom line is CH3 dot plus Br dot goes to CH3Br. And this is just the way the reaction finishes. And that leaves us about 10 minutes once you've written that to play a little game. This is a way of practicing this. And I'd like you to get in groups of 3, I get an A4 bit of blank paper, but I want you to be in groups of 3 with people you don't normally. In fact, I'm going to talk out the groups. I'm going to stop the video because that'll do. for today, but we'll practice for the rest of the lesson.